As you can probably tell from the title of this video, we're going to be looking at how to solve a problem called string matching using a finite state machine. A brief overview as to what will be included in this video is as follows. Firstly, I'll go through a very simple algorithm called the naive algorithm. I'll then move on to the main topic of the video and explain how to use a finite state machine for the problem of string matching. For the last minute or so of the video, I'll move on to explain the computational complexity of the different algorithms I have discussed and other algorithms you can go look up after you finish the video. But first, let's answer the question, what is string matching? String matching is used in a wide range of areas. On web pages, when looking for a specific word within a large web page, within computer science, when searching for appearances of certain functions in a large piece of code, or even within biology, when searching for a small strand of DNA against the DNA of an entire animal or plant. String matching is simply just the name of trying to find all the occurrences of a specific string within a larger string. For example, take a string which we want to find within a large text, in this case BBA. This is called the pattern. Now we have the pattern, we need a large string to search for the pattern within it. This is called the searchable string. As you can see, BBA appears twice within this string, here and here. In this simple case, it is very easy to find the pattern, but when dealing with much larger cases, how do you go about this in a quick and efficient way? The first algorithm I'm going to show you is called the naive method. This method is a very simple method, but it still takes a very long time to process. The naive method works as follows. It takes in two input strings, the pattern and the searchable text, and begins to compare the two strings at the first character of each, moving along character by character, checking each letter against the other. If at any point the characters do not match, we move the entire pattern or one character along the searchable string, and the process is repeated, this time starting with the second character of the searchable string. If you manage to reach the end of the pattern string, then therefore you have found a match, and the position is outputted. This is repeated and continues up the searchable string until reaching the n-mth position, where m and n are the lengths of the pattern and the searchable string respectively. Currently, in the center of the screen is a pseudocode to the naive method, which we'll use to work through the following example. Take these two strings, the pattern, ABBA, and the searchable text. The naive method firstly stores the size of the pattern in M and the size of the searchable string in N. It then enters the loop and begins comparing strings, starting at the beginning of the searchable string. It does this character by character, so A checks against A, that's a match, and B checks against A, that's not a match. Therefore, the strings don't match and the pattern can move along the searchable string. The pattern continues up the searchable text where it reaches a string which matches the pattern. Here the position is outputted, in this case 5, and the pattern proceeds up the searchable string. This repeats until the pattern reaches the end of the string. As you can see, this is very inefficient, making 24 comparisons for a searchable string with a length of only 15. Next we'll look at a quicker and more efficient way of searching for a pattern within a searchable string. This algorithm is called a finite state machine string search. The finite state machine string search works by taking in two inputs, the pattern and the searchable text. Next comes the most complicated part of the algorithm, which is that the algorithm creates a finite state machine which moves to an accept state when you see the pattern within the regular expression inputted to the finite state machine. We use the searchable text as a regular expression which the finite state machine takes in and begin to process the regular expression through the finite state machine. Each time the finite state machine reaches an accept state, it has found the pattern and therefore the position must be outputted. The finite state machine then continues to process the remainder of the searchable string. The algorithm terminates when there is no more of the string left to process. A finite state machine is defined as shown. It has a set of states, Q, a start state, Q0, which lies within Q, and a set of acceptance states. The alphabet of regular expressions is given by the set sigma. Finally, delta is a function that takes in a state and an element from sigma and returns another state. Now let's look at the pseudocode. Using the upcoming example, we will work through and analyze this code. Firstly, the algorithm takes in two inputs, the pattern and the searchable string. As we can see, we are using the same example as before, so it makes it easy to compare the two algorithms. Next, we will store the length of the searchable string in n, and we begin to build our finite state machine. We start off by building the path which would accept the pattern, going from state 0, adding A, B, B, A as transition characters through to the fourth state, as shown, making the fourth state our accept state. Now we need to add the other transition functions from each state. For the 0th state, we need to add the transition function for the character B, which returns back to the 0th state. The first state, character A, which again returns back to itself. The second state, A, returns to the first state. And the third state, B, which returns back to the beginning of the 0th state. For the final fourth state, we need to add both A and B as transitional functions. A returning to the first state, and B returning to the 0th state. Next, the pseudocode for the algorithm tells us to enter the loop and begin processing our regular expression through the finite state machine. In this case, our searchable text. We enter the finite state machine at the 0th state, the start state. From the regular expression, we read in A and follow the transitional functions to the first state. We then continue to repeat this process character by character of the searchable text. Upon reaching the accept state, the algorithm tells us to output the position within the regular expression as it has found the pattern within the searchable string. In this case, the position refers to the end of the pattern, unlike the naive method, which returns the position for the start of the pattern. It then continues to process the remainder of the search string until reaching the end of the text, at which case the algorithm terminates. Compared with the naive method's 24 comparisons, the finite state machine search algorithm completes string matching in just 15 comparisons. Now let's take a look at the computational complexity of both algorithms side by side. As you can see from the table, for performing the string matching, the finite state machine string search is computationally much quicker in the worst case. Although the main disadvantage to the algorithm is that it has a fairly large pre-processing time, which is big theta of the length of the pattern multiplied by the size of the alphabet for the regular expression. There are many other algorithms out there, and a couple of the most used ones include the North-Morris-Pratt and Boyer-Moore-Horsfall algorithms, both of which have benefits and disadvantages compared to the finite state machine algorithm and the naive method. I hope you learned something from this video. Thanks for watching.